Thank you. Thank you, Angela, for kind words, but she did all the work. So I'm going to start first. We're all here to celebrate how, everything is physics, right, that we do. But except you never want to trust us to make a machine or, play. There are a few who can actually do it. So this is why we call the professionals. And we can just sit and calculate the equations, how, formulas work and what frequencies come out of the instrument. But we're going to leave to professionals, as I said, to play. And so we're going to start with music. And the reason why Adrian is here, as you can read, he's a very accomplished performer. But there's another reason, actually, why he's here, other than being really sought-after classical guitarist. When I first met Adrian, he told me his story. And he said that when, he was 7 years old, when he really, wanted to get his first guitar and play and passionate, and people told him something that a lot of our students can relate to, that he shouldn't play a classical guitar or dream to be a performer, because that's strictly reserved. That's an instrument of Spaniards, Europeans. And if you're not that, then you shouldn't play a guitar, classical guitar. And of course, Adrian kind of has the same mentality. I think this is why we connected and said, well, I'm going to show you all wrong, and I'm going to try to become the best I can. And I know that his dream is if everybody could just leave him and he could practice guitar 12 hours a day, he would be a happy man. And I'm going to show everybody, that I'm going to become the best, and I'm going to play all these, European composers. And if I do become a best and people appreciate me, they will compose for me. So his dream really came true. He's been really promoting Latin American music, classical guitar music, that's been really composed for him. And also, what is his endurance or persistence really paid off. That he's actually famous, what I heard lately in guitar among composers, that you find a guitarist, usually they want the piece to be composed 6 months or a year before they have to perform it, but in the circles he's known as a lunatic in a really good way, because you have to give Adrian a piece 5 weeks before and he can actually perform it perfectly. And anyway, without further ado, I'll stop. Let's listen to Maestro, okay? Thank you.
Well, good afternoon, everybody. It's a real pleasure to be here with you, sharing my music. Thank you so much, Vesna, for inviting me to be here and for your kind words. Today, I'm going to start with a piece that is actually going to be two pieces into one. It's going to be the Adagio of the Violin Sonata in G minor by Johann Sebastian Bach, paired with the Serenade by Sofia Guaidolina. And the reason why I'm doing this is, although I'm not a religious person myself, I grew up into a Catholic environment. And praying was a really important part of growing up in this environment. And the way they connect spirituality between the praying act and the family and coming together really inspired me in a lot of ways. So I think, Bach is well known because his deep connection with God. So I'm going to pair these composers because both of them, they are really connected in that sense. Also, they have a really perfect sense of structure. And also, you can always find as well the fight against the darkness of this chord, that both pieces start with the same chord, and then they end with a major chord. So we are going to travel in time and through darkness to find light at the end. So Adagio by Johann Sebastian Bach and Serenade by Sofia Guaidulina. Thank you so much. I promise that the rest of my part will be more uplifting. The second piece that I'm going to play is by a Spanish composer, probably the best guitar composer ever. The only problem is that he didn't know that because he composed everything for piano. But I promise that it sounds way better than guitar. So this is a piece that is really famous into the classical guitar world, not so much into the piano world. And it's composed by Isaac Albéniz, who was a Spanish composer who lived in France, and he composed this during that period. He teaches at the Conservatory of Paris. And the first part is, like rhythmical, uplifting, full of energy. The second part is more like his sadness of being away from home. So it sounds a little bit more like the cante hondo, that is like the traditional form of singing of Andalusia. So it's an ABA form with a chord at the end. So the piece is called Asturias by Isaac Albéniz. Thank you so much. To end my presentation, I'm going to play a piece that was composed recently. And I got called lunatic because of that. And I've been called lunatic in my life for several reasons. And in this case, it was for a good reason. And I think it's a perfect way to end my presentation. And I have to be honest, it was quite frightening to perform today. Because, well, I'm surrounded of really amazing, talented, and smart people. I'm just a guitarist. You know, when Veshna asked me, hey, can you come and play? And I said, yes, to the physics department. I was like, oh, all right. Because, well, I can fairly say I can play guitar, but no more than that. But this piece is called For Those Who Dare. And it's somehow inspired on my life journey. So I want to end with that, a really uplifting piece, trying to share that, right? Like always, I mean, life is for those who dare. That's why I'm here. So I hope you enjoy.
Thank you so much, Adrian. Let's give him another hand. That was beautiful. Thank you. Okay, next we have Leland Baker, and our very own Stefan will be accompanying him on a couple. Oh, you'll introduce him. Okay, got it.
Stefan will accompany
Will
him, but
accompany
he'll
him and
introduce
introduce
because
him.
He knows, yeah.
Yeah, go ahead.
Everybody knows his personal story.
Wow, Montero has two brains. That was a thought that was going through my head. That was amazing. Give it up to him. Oh, no, that was amazing. Huh? 10 fingers on, only 10 fingers on each hand. But I thought I heard, when I closed my eyes, I thought there were two people, a person snuck up on stage and was playing along with him. Wow, I was blown away. So it's my pleasure. Pretty soon you'll know who I am, for those of you who don't know who I am, but that's okay. It's my pleasure. It's just like a tremendous pleasure. When I moved to Rhode Island 8 years ago, I heard there was some person that we're referring to as the young John Coltrane. It's like, I want to know who this person is. And then I heard him. And at that point, I bought my own instrument to come to this particular jam session, and I put my horn down and just proceeded to listen to him. And now he has pretty much been leading the jazz scene, one of the leaders in the local Providence jazz scene. After doing a stint in New Orleans and New York City, where he also established himself as a jazz saxophonist. And recently, I actually saw him at the International Newport Jazz Festival play, where he's also runs the Newport Foundation. You can say a little bit more about that. It's our great pleasure to have Leland Baker.
Talker. Can you hear me? Hello. Okay, there we go. But thank you, Stefan, for that very gracious introduction. It's a pleasure to be here. Yeah, I'm a saxophonist, a jazz practitioner, enthusiast, and educator. And when I was asked to come here and do this, maybe kind of like Adrian, I was like, why am I being asked to come to this physics thing? But I'm excited to be here because a lot of the guys I admire and who are true icons of this art form we call jazz, or I like to call Black American classical music. John Coltrane, Thelonious Monk, they maybe didn't know the inner workings of physics like you all do, but they knew that there was something about music and the vibrations and the frequencies and these formulas and structures that we work within, and we also work to break and to learn more about. So anyhow, I'm gonna do some free improvisation and kind of use the form of a tune by the great Thelonious Monk called Ask Me Now, and then I think we'll have the great Stefan Alexander and another friend of ours come up, Jesus, and jam out. And I just hope that you all could, as I'm playing, really think about frequencies and these vibrations within each note and the registers and all this that I'm accessing to create a mood and a sound.
Mm-hmm.
get Stefan and Jesus maybe to come up. Yeah. Say
Words
something.
by Jesus. So it's also, whoa. Whoa. I don't want to play now. I'll try though. I'll try to hang. It's like a real honor and a real pleasure, and it truly is an honor to have one of the great international Latin percussion masters. You know, we're so lucky to have him here in Providence. He's played all over the world. He is from the Dominican Republic. His name is Jesus Andujar. Jesus, am I pronouncing your name correctly? Okay, I finally got it after all these years. And we're in for a real treat. This is, I guess, is going to be, we're just going to make this up from the top of our heads, right? You're going to call a key, and we'll see if I can hang. I'll let you set it off.
He's setting up to talk about a little bit of what just happened. Some things, there was certain, it was free and in the moment, of course, but there was some, you know, some devices that I was using in efforts to try to create something and get somewhere. And these things called enclosures, it's kind of like trying to produce, vibrations. I mean, each note has a vibration, but multiple notes at once. Within kind of a flurry of sound, kind of like a sheet of sound, which actually John Coltrane, one of his periods of playing was known as sheets of sound, when he was really getting into just playing a lot of different scales, a lot of different sounds, very fast, but all in efforts not to show off, you know, in terms of his technique, but to, you know, really explore sound. You know, as musicians and jazz musicians, you can get deep into improvisation and the language and all the bebop and all the heady stuff, but, you know, not just about each note or harmony, but the sound itself, how to manipulate sound. So that's kind of a device I was working off of, and I tend to explore a lot. Anyhow.
Let me an A or B. Just your B. You set up a rhythm.
Can we just go back? Yeah, just go back.
Oh, you just wanted
Yeah,
to
just go
do
back to
this.
music. Go to music. Yeah. Go to arts. Go to arts and plug it in. Okay, so we're going to go on to arts, and Vesna will introduce the different presenters.
Okay, so we're going to continue with frequency here. Okay, that's the theme of the night. And now from sound, we're moving to color, light, I guess much higher frequencies. And we're going to invite our artists, maybe if you want to take a podium. And first is, so two artists here are expert on color theory and can probably teach classical optics better than any of us in physics. And let's invite the first, Leah Beeferman, who's a professor at RISD nearby. So please.
All right, and that was PowerPoint, right?
It's a keynote.
Oh, Keynote, perfect. That makes it easier. Thank you. There we are. That must be it. Oh, nope, that's right. Yeah, so it's Keynote.
It's one of the key ones.
Is it one of these?
It's a Keynote, I guess.
Search the name.
Okay. They should all be up here, right? Okay, is it physics? Is this for me? Or yep, so it's still on that.
Oh, it's right. It's right here. This one. No, it's still downloading the one below. That should do it.
Okay.
And then just go to the top. And then just pop it back in.
To present, right? So
Yes.
here we are.
I was told actually while we're trying to figure out the slides, if it's not too, no,
Oh, I think we figured it out.
I was asked to actually introduce the next speakers.
Oh. Okay, so I just used that.
Yeah, right, is advance, and you can also advance that.
Okay, perfect. Okay. Hello, everyone. Hard acts to follow. That was great. My name is Leah Beeferman. I teach at RISD. And I like to start my talks with this photo of me doing what I like to do, which is photographing things up close. That's one thing I like to do. Up in northern Finland, way up in the Arctic, which I'll talk about more in a minute. And just to put these up, you don't have to think too hard about them right now, but these are some questions that have guided me along the way. And some key words here that I'll kind of come back to: science, abstraction, quantum physics, empty space,
real world, weather, observation, measurement, and images. And all of these are things that I have big questions about, and I explore them in various ways in my work. So I'm going to start, and my captions are a little off, the font didn't come through. But anyway, I'm going to start, these are some brand new pieces that I made, I guess, last year. And they go back to a process that I developed about a decade ago, where I cover sheets of aluminum with graphite, and then I laser etch images off the surface of the metal. And they are combining some scientific images with some digitally drawn abstract marks that I made. And it's kind of obscure which one is which, although you may be able to tell. Some of the imagery is from NASA, some of the imagery is from NOAA, and some of the imagery is mine. And this is one of the kind of original pieces back from 2011. And it started to explore this first question that I had, which I sort of arrived at looking at scientific graphs that I just was interested in visually. And I was thinking, you know, if you're a trained scientist and you look at a diagram or you look at a graph or you look at a scientific image, if you're trained in that field, you probably know exactly what that image is trying to tell you. But if you're not, then you don't know what it's trying to tell you, and it's just an image. And the image is therefore possibly quite abstract. And this really struck me at the time, that something that was information could also be something that is abstraction, depending on who you are and what you know and how you're looking at something. And this is one of the key questions that has stuck with me ever since. So in 2012, I was very lucky, I went on a residency research trip to Svalbard in the Arctic, and this is me looking very cold and really dumbfounded at the time, which I was. And we were up here, outlined in red, Svalbard. It's like up near the North Pole. And before the trip, I had been reading about quantum physics, which is something that I'm interested in, although I don't know nearly as much about it as you all probably do. And I was really struck by this idea of empty space, and that empty space is not actually empty, it's actually dense and quite turbulent and active. And I was sort of trying to figure out how does one make sense of this? That's something that happens at a scale that we can't experience. But supposedly science is telling me that it's true. There's something sort of abstract about that idea because I can't see it, I can only imagine it. And I was trying to figure out how do I understand that? And when I got to the Arctic, all of a sudden I was in this place that was so cold and so still and so big and open that it felt totally empty. There was barely anything moving. And at the same time, the ice was really dense, the landscape, the mountains was super dense. There was a really supercharged energy that felt also really dense, and then my experience of the whole thing was also very dense. And I started to think, wait a second, this place is a manifestation of this idea. And from there I got excited about the possibility that I could look to understand these abstract ideas that I could never understand through my own experience, sort of by proxy in terms of what I was looking at in the world. So I started making some pieces. These are some early digital prints. They're hard to photograph. They're very glossy. They're on metallic paper. They're using sort of pieces of photographs that I took in Svalbard alongside some digital marks, and then solid, quote-unquote, empty digital color. And so this kind of triangulation between, empty digital space, emptiness and density, and then the Arctic became something that then took me forward. And this was a not a huge series, but there are a bunch of pieces, so just to show a few of them here. And I'll talk over this. I was really interested in this idea. I still am, this kind of emptiness and density paradox. And I made a kind of performance event, which was comprised of a 10-minute video or 11-minute video, a text that I wrote that I projected and sort of scrolled through, and a sound piece that I made. And the video here sort of takes a similar logic of the digital empty background. These are images that I took, or videos I took from NASA of solar flares. There's also some footage of volcanoes erupting and some footage of water that I shot in the Arctic. And sort of this rotating square, which is this perfect geometric form, trying to kind of encapsulate this natural phenomenon. There was something about that for me of what science was trying to do to understand the world. And so I've shown this piece many times, but one version of it that I have decent photos of is this one in New York in 2015. And the text, I wish I could show you the whole thing. It's sort of fun to make people sit for 10 minutes in silence and read about empty space. But, it starts here, me trying to explain this idea, and then it goes into sort of how this idea relates to the landscape, and then again into the idea of how empty space is not vacant, it's actually full of potential, which was an exciting idea for me to think about at the time. So jumping ahead a little bit and going back to Finland, where that first picture is from, I've spent a lot of time in Finland. I did a Fulbright there, and I've gone back many times. And this spot up in the Arctic, on the border of Sweden and Norway, is a place called Kilpisjärvi, which I love very much. And I'm going to talk over this video, so hopefully the sound will be okay. I made this piece in 2019, and this sort of carries over my question of what it means to observe something and what it means to measure something. And so obviously, if you are measuring something in a lab, you have the tools that you need to measure that thing, or you figure out what those tools might be. But trying to measure something like a landscape is a little bit more complicated. And I was really interested in the idea of this kind of abstract measurement question of how can I measure, how can I record this place that is totally four-dimensional, totally time-based, way larger than I am, and changing all the time. And so in June in Finland, in this part of Finland, the sun doesn't set. And I was really excited about trying to document the light that was changing sort of around me as it reflected in the lake and on the mountains around the lake. And so the shapes here, again, are me trying to abstract something that's familiar so that you look at it a little bit differently than you might normally. The different sort of sections are the different times sort of successively overlapping one another. So over the course of 15 minutes, you see clips or sort of shots from the whole 24-hour cycle from 1 in the morning until 1 in the morning. There's 3 versions of this video with sound done by 3 different sound artists. This particular piece is by an artist in LA named Byron Westbrook, and he composed his soundtrack entirely of different frequencies of sine waves going back to the sound kind of question. And it's a really exciting piece to hear on its own at a better volume than it is now. The same year, I was lucky to have the opportunity to also go to Ecuador, and I was sort of, I went from one scientific research station in the Arctic to another biodiversity research station in the Amazon. And the Arctic, with its own kind of questions of emptiness and density, all of a sudden started to feel incredibly empty when I got to the rainforest, needless to say. And I was sort of thinking about the same questions. It was the same year. The impossible task of trying to document these incredibly important places in the world, on the Earth, and then the rainforest being so dense that there's really no way that you could possibly record it for different reasons than the Arctic. And I made a video that's 30 minutes long. I'm going to show a short clip basically talking about that impossibility. And then I'm not going to talk over this. You can turn the sound back up.
What is a viewer to this place? Is a viewer a participant or someone at the surface who looks? The creatures move through the gaps in the surface, the spaces between the leaves. I move through some of the gaps, but I am looking into and at. Buoyant air makes thunderstorms, and I am looking in time. I look at one time, I look at another time, and at another time. I look in time. What is shown to me that I might not notice? What did I not see because I looked away? And what resides or hides behind the surface? It's impossible to see everything at once. It's impossible to see everything ever. To try to look at one thing, to try to isolate from density. I don't know how to locate the birds across the canopy, to find them in the branches of the trees when there are so many trees. Imagine if the trees continued forever like they probably used to, between winding rivers of blues and browns. If the trees continued forever, perhaps the birds would continue forever, too.
So I'm going to skip this for time, but I want to end on some also recent work that goes back to this idea of the weather and to scientific images and imaging. And these are some 3D pieces that I've started working on in the last year, combining different satellite images and weather maps from the EU and from NOAA, and then some digitally sculpted shapes that I have made myself and have all of these different elements kind of casting shadows on each other, like clouds casting shadows down on a landscape. And I think that, in the idea, or alongside the idea that that the weather is something that is kind of constantly changing the way that the landscape looks and feels. It's also a really interesting kind of question or problem to me about how we make sense of the weather itself. So that's kind of where my interests are taking me now. But all of these different imaging systems that we use to sort of capture different elements of the weather and map them, they're their own kind of version of photographs where they just take one isolated moment in time and sort of, unless you're looking at it in sequence or unless you're looking at it in larger context, it's again sort of just an image. So I'm really sort of excited about the way that images function in science as compared to how they function in art. I think there's a lot of overlap and a lot of difference, but there's a lot of really exciting questions in there for me. So thank you very much.
So I can introduce the next speaker while we're waiting. So next, we're going to hear how to use science or information theory to value art. And the reason, so I would like to welcome Jelena Berenc to a podium, but just to kind of, on a side note, there is ulterior motive why she's here. Our department actually hosted a QVIP, which was conference for undergraduate women in physics, and she was invited by our late chair, Minashi Narain, to perform 3 workshops during that conference. And while she talked about art, she actually had these papers that we had to provide to everybody, and people were asked to listen to her lecture. Some of it you might hear today. And they were asked to actually draw this continuous line, random, and not looking at it, right? Completely unconsciously. And the point was to, at the end of it, most of people have drawn about, approximately 5 kilometers, or if you prefer, 3 miles. I refuse to use anything other than SI units as a physicist. So people were really amazed by what they created. So I guess her message was a little motivational to show that, hey, look, everybody can become kind of an artist. Or also, if somebody tells you to do something, we are so programmed to think that it's impossible when we hear these big numbers, and yet unconsciously, she can make you do it, right? So anyway, without further ado, I call Jelena to podium. Yeah. Thank you. Yes. It's a PowerPoint. That's it. And there's a little video at the end.
Okay. I'll stay close to make sure that works.
Thank you. Thank you. When I was growing up, I had to share my room with my sibling who had monopoly over it and whose untypical sense for interior design resulted in our walls being covered with posters not of the superstars, but real stars, galaxies, and nebulas. And we both stared at those walls countless number of hours, and they transformed into these endless, infinite worlds. And we wondered the exact same question: what in a world is all of this? And we devoted our lives to it. My sibling is a physicist, and I'm an artist. In my sibling's lab, full of metal and liquid nitrogen, the experiments are set up to test the question and confirm the answer. In my studio, I set up an art process and by the way, my studio is full of carbon, pencils and paper, to experience the question, to understand the answer. But both art and science, they question the world, and they offer us new ways of seeing it. And to illustrate that, I'm going to read a following quote by Carlo Rovelli. Artistic thinking explores and redraws the world, gradually offering us better and better images of it, teaching us to think in ever more effective ways. Art is a continual exploration of ways of thinking. Its strength is its visionary capacity to demolish preconceived ideas, to reveal new regions of reality, and to construct new and more effective images of the world. This adventure rests upon entirety of past knowledge, but at its heart is change. Now, Carlo Rovelli, being a theoretical physicist, of course, didn't talk about art. He was talking about science. I just replaced the word science with the word art. But we can see that in both cases, this definition perfectly, most accurately defines both fields. Erwin Schrödinger wrote in What is Life, that over time, over centuries, we inherited this universal, all-embracing knowledge that is the only one with the full credit. But the extent of knowledge forces us to be more specialized and more narrow, which perhaps it's time now to be more comprehensive with our representation of reality. Patrick Kavanagh is a leader researcher in visual neuroscience and perception, and he noticed that art is 40,000-year-old record in experiments in neuroscience. And it tells us as much about human brain as it does about world around us. Roberto Zenet, Brown's own professor of engineering and research in fluid dynamics, has studied extensively two brilliant artists, David Sakwaro's and Jackson Pollock's painting processes. And he noticed similarities in different areas, like lava domes on Venus, as well as Great Kavari Desert, Salt Desert in Iran. In Iran. Now, art, that type of art that perfectly captures this idea of universal knowledge, is something that I like to call information realism. It is a type of art that questions the world, restructures it, but most importantly, through its processes, through the relations between informational units, captures information from reality verbatim, without any influences from artists' beliefs, opinions, or expressions. So to illustrate that, I'm going to show a couple of examples. I think this is the very first information realist piece because it captures through somebody's physicality, information and documentation of somebody's presence in a moment at the moment. Similarly, we have a contemporary artist, Ondijk, who starts his piece with the empty gallery. And the gallery attendant would mark every visitor's height, name, and the date. And the gallery starts transforming from these random marks into this collection, almost like interference pattern at the end of the piece. Now, Dada is a nonsensical art movement that started in 1916 in Zurich, in Switzerland. And they started as a reaction to the World War I. And I call them realists because if you think about it, at that time, the world made absolutely no sense. everybody was using very rational reasons to justify very ill-conceived actions. So how do you capture the world on a realistic way when it makes no sense? Well, make art that is nonsensical, irrational, and illogical. Interestingly enough, at the same time, great minds like Max Planck, Dirac, Bohr, or Louis de Broglie, Schrödinger, Heisenberg, just to name a few, they were working also on a very nonsensical idea of quantum theory. At the time, it didn't make any sense, and in order to be understood, required a great amount of abstract thinking, knowledge, and intellect to be understood. Cornelia Parker's work captures literally the objects and their remains after the destruction. Like exploding shed that we see on the top, it is an explosion captured, frozen in time, or the house that is destroyed by the landslide, or the church that burned down. Charles Ross, who interestingly enough has a degree in mathematics and physics and then turned to sculpture, was burning the planks of wood by concentrating the sunlight with the lens. It takes 8 minutes, 33 seconds for a photon from surface of the sun to come and burn this plank of wood. It is sun making a self-portrait of itself. It's a phenomenon captured by the phenomenon. And he did this every day for a year. Talking about the space, Rachel Whiteread pours the concrete into the building, tears down the walls, so that space itself, the air itself, becomes visible. We know that it's a fundamental part of everything that is micro and macro, so it is making us aware of that space. William Anastasi has a very simple rule. Take a same commute, paper on a lap, pen in each hand, and closed eyes. And then the train itself will make the drawing of its own experience, because the movement of the train would make these drawings. And of course, taking a function out of the object, flipping it around, the identity of something, flipping it around to make us more aware of that identity. So flat iron, supposed to be flat, now we have nails, or the umbrella made of sponge. Now, some personal examples of my work. What is time? I know what it is, but I really don't. So I wanted to understand it, so I made 1,440 squares daily for a whole year. And I colored in the number of squares that matches the number of minutes that I've been awake. By the way, that number means how many minutes are in 24 hours. So pretty much documenting every single minute in a year. What is million? No clue. So I made 1 million bricks. Now I know. Takes a long time. 10,000 it's a book of all, or book of 10,000 drawings that consists of animals, plants, rocks, and places. It is a book of just collection of perceptions. 100 drawings of flowers are made on 10 by 10 pieces of paper. As soon as they're completed, I cut them into centimeter by centimeter squares, totaling 40,000. And then I randomly reassembled them back, all those 40,000 squares, onto 100 10 by 10 pieces of paper. I wanted to see what does randomness do. 40,000 factorial is a staggering number, and this is just one combination of it. What's going to happen? This is just one piece out of 100. Would there be collection of more material and less? Would it be even? I didn't know what to expect. It's an image of interpretation of the universe, so it's a mosaic installation of hundreds of little tiles, but it's made with water and chocolate powder, water that is invisible, completely dictated where the charcoal powder is going to collect or not, and on which particular way, almost like invisible dark matter that dictates how the matter is going to collect in the universe. 4% is all we know about the universe. The rest, we have no clue what it is. It bothered me knowing that fact. So I made a book that is 1,000 pages long, and it's completely empty except 40 pages that are filled with these bit marks. This is one of the pages that are at the beginning. And that book is really, really empty. Another one that I was really interested in is these involuntary actions that keep us alive, but we have no clue, we're not conscious of it. So 100,000 heartbeats in a day, in 24 hours, that keep us alive. So I made a book that is the size of the average heart, somebody my height, and I made 100,000 watercolor marks in it. Understanding self. This is a portrait. One side of the glass has a number of marks that matches the number of days that my mom been alive and up to this point, and then the other side, my dad. It's defining yourself through every single day that your parents lived to kind of compose you, who you are. This is a 1 mile long drawing of portraits. It is unofficially the longest drawing in the world, and it had to be that way so that it can work with the concept. And it's installed in these film reels. It's a collection of, I call them self-portraits. There's a video that I hope we can play. No? Anyways, in order to see the drawing, you have to roll it from one side to another, and you can only see so much at a time by interacting with it. It's almost like a superposition of all the possible possibilities that you can have, and by interacting with it, you collapse it into only this one option or one interpretation of it. And this is a 40-hour continuous line and 30-hour continuous line. Now to conclude. How do we judge or determine the value of art? Simply by applying physics and information theory to it. I propose that we can do that. We can determine the value of art simply by determining how much information it carries. Ancient Greeks suggested that the information of an event is directly influenced by how probable that event really is. Even Aristotle suggested that more surprised we are by an event, more information it carries, which means that information is inversely proportional to the probability. If the probability is low, more information, vice versa. And more information, more quality to art. If we have a painting of a cat, very realistic painting of a cat, just imagine it. No Schrodinger's cat, so no mystery if it's alive or dead, just fluffy, beautiful cat. And we look at it, we all know what it is. We're all going to agree upon that. There is no other interpretation of it. It's just the cat, meaning there is no value to it because information is low. In contrast, if we look at Rachel Whiteread's The Concrete Air, or if we look at the iron with nails, it's surprising, the explosion frozen in time. It is surprising. It's a complex piece that for all of us can have some kind of other meaning, right? So the information is high, meaning the quality of an art piece is high. This view I adopt from Vlatko Vedral, who is information quantum physics professor at Oxford, and of course Claude Shannon, the father of information theory. Because after all, physicists and engineers are artists who are just really, really good at math. Thank you.
And now we're going to segue to a real physicist and artist who also use carbon. And I have to thank Leo, my dear colleague, who making every proposal so much nicer to read the look, because every time I need a pretty picture, I call him, because he's really an artist of representing our physics devices.
Thank you. Thank you so much. And then here's your okay. Hello? Can you hear me? Can you hear me? Okay, great. Thanks, Vesna, for the introduction. It's an honor to be here. I'm a physicist here at Brown,
So I'm fairly used to talking about or giving lecture about physics, but this one, right, gave me a brand new challenge, because it forces me to ask the question, what is art? So here I'm going to give you a physicist perspective of what is art. As a physicist, I use art very often as a tool, right? It's the most convenient tool to talk to people, to communicate with people about what I'm thinking. Sometimes this could be a little abstract, but using art, it becomes much easier. To give you an example, this is the course description of one of the core courses. Roughly speaking, it's about electric and magnetic fields, right? You can read all the rest, but that creates a barrier in the communication, right? So a few years ago, I did a poster for the TA who wants to let people know that they're the TA for this course. So this is what I did. For some of you who don't know the details, right, this is a Poke Monster, Pikachu, and their power is electricity, lightning, right? And the Pikachu holding a magnet just give you a direct image of what this course is about, electric and magnetic field, right? And art is also a great way of talking to people about what research I do. I work with these materials that only has one layer of atom, right? And the size of the material is about 100 times smaller than the width of your hair, right? So it's kind of impossible for me to hold up my device and show you here, this is what I do. But what I could do is something like this, right? These are layers of atoms, and these are atom electrons that move around these layers. And what I do here is that I shine photons, particles of light, onto it that are these, and their interaction kind of tell us a lot of stories about what nature is doing, what the universe is doing. Okay, but it doesn't really address the question, what is art, right? Knowing how to use it as a tool is nowhere near getting to the bottom of this question. However, as a physicist, I have years of training to try to solve a problem, right? So here's what I did. I typed into Google, what is art, right? Usually that's the first thing we do. Google tells me that art is the expression and application of human creative skill and imagination and blah, 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 right? Words are not incorrect. It just doesn't really carry the meaning of what is art. It doesn't carry the weight. And this is when I realized that in order to address this issue, I have to step out of the physicist. I cannot be a physicist to think about this. I have to go away from work. And away from work, sometimes I draw as well, right? Just old-fashioned pencil to paper. And when I feel like drawing, my family usually is the target or the subject. And so I didn't do a glamour shot. These are just when they're still on the easel. But each drawing takes about 50 hours. And I enjoy doing that. It's not really about the artistic technique. It's not really about the outcome. It really is because I have a feeling, a strong feeling that's abstract, that's personal, right? That's emotional. And I feel like translating that into something that's visual. And when my family sees this, they kind of know how I feel, how strongly I feel about everything, right? It's this translation that makes me feel really calm and occupied when I spend these 50 hours. And so this is when I realized there is a very strong parallel between art and physics. I can kind of use this to both explain what is art to a physicist and also what is physics to a lot of people, right? So physics is not completely abstract. It is governed by a set of principles. These principles, we can come up with them, we can prove them, and we can do experiments to verify they're true. For example, there's a very famous phenomenon called quantum Hall effect. They can be expressed very elegantly by a set of equations. They can even, depending on what model you subscribe to, you can use different equations to describe them, right? If you look at them long enough, if you know what you're looking, they're elegant. But my family assured me they're definitely abstract, right? It's very abstract. And what we do, what my research does, is these equations tell electron what to do, and we can kind of measure what electron does, and that's what we do as experimentalists. So this is kind of the translation of those equations into actual measurement. Let me explain what you're looking at, right? Each pixel is a number, and instead of showing you a number, I give it a color, right? Red is a very large number, and blue is 0, right? So when you do that, all of these patterns come out, and these patterns means a lot to us physicists, and to most of other people, it's artsy, right? So there's a little bit of parallel in there. Just like the drawings, it takes some time. This took a little time as well, right? It took us like 5 or 6 decades, 3 Nobel Prizes, and a little bit of extra work to make this happen. For example, this feature is 1 Nobel Prize. That is another Nobel Prize. And the material itself is another Nobel Prize, right? And on top of the 3 Nobel Prize, we did another 10 years, give or take, of extra work. In order to make sure this presentation is true to the reality, let me give you a bird's eye view of what the process that 10 years is roughly about, right? So when students or researchers from our group try to do this experiment, they start from the lab. They're going to spend, I don't know, 30, 40 hours in the lab, depending on how good they are. And then they go through go into the clean room and use a set of these fairly fancy, definitely expensive machines. And when they have a sample, right, they load them into this cryostat in our lab that can cool it down to almost absolute 0 temperature, where electron behavior start to match the equation. Sometimes they have to go to the National Magnetic Field Lab. The equipment here actually several buildings tall. It's all underneath this platform. And this entire long probe had to go all the way down in order to access it, right? So with all that context, right, that adds the meaning to the art or physics that we're doing. So since I'm talking about this, I should also acknowledge that I'm not the one doing the work, right? So I do need to shine the brightest spotlight to the people who actually did the work, right, in my group, who go through all these processes to translate the abstract principle into the art or physics itself. And they did a lot of really hard work. They learned some. They had some confusing discussion throughout the process. I think they also had fun. It's a privilege to watch them go through this process, have fun, and enjoying themselves grow as a physicist. They are literally rocking it as they slowly become the exceptional physicists they are. And so that's my story about art and physics. Thank you for your attention.
Okay, thank you, Leo. This is perfect continuation. Now we're going to physics, and it's really my great honor to invite Jim Gates, our colleague here, and he's a theoretical physicist, so he will tell us about the great ideas of the universe, or I better stop and let the master speak. Okay.
Well, good evening. Let's try that again. Good evening. Good evening. Thank you very much. It's my very great pleasure to be here, to return to Brown. I was a faculty member here for 5 years or so, and unfortunately, due to the COVID epidemic, some things happened with my wife that caused me to retire from here, but I regard this as my second home, so I'm very happy to be back. Had a great dinner with colleagues last night. So what I wanted to do, let's see if we can get this to work, is to start here. This is in fact one of my favorite pieces of music, Rachmaninoff's number 2. It starts off with a very driving sound, and I didn't actually record it, but it's a favorite of mine. Now I wanted to start here because of the following. I bet none of you are afraid of this. Is that correct? What about this? You see, we live in a world where most people know that music exists in 2 forms. It exists in the form that our performers here demonstrated on the stage, where you have an immediate emotional reaction to their actions. But music also exists, as you know, in this form. So imagine a world where there was no sound. Could music exist on that world? My claim is yes, because a small group of people might learn how to score. And they would talk about the power and the majesty and the beauty of these symbols. Now, the rest of the population would, of course, wonder who are these people? And they might call themselves the musicians. And that's the world I live in. You see, what I do is exactly that story. There's a kind of music that we physicists are engaged in, and it is, in fact, the most effective way to communicate that. I learned, just as this speaker just in front of me, I learned in 1988 that the most effective way to talk to people about physics is not to show them this, but instead to show them the stories that correspond to the music that comes out behind these kinds of things. So I'm going to introduce you to Einstein's opus. You know, if it was Beethoven, I might say da-da-da-da, and you would know immediately what that was. But this is what Einstein's opus looked like to Einstein in writing a set of equations. It's a score, but it's a score of the music that nature herself plays. It turns out that mathematics is both exotic and exquisite. It's exotic because so few of us speak it very well, or if at all. It is exquisite because it is apparently the only human language that allows us to have an intimate conversation with nature. So it's a very strange thing. And we believe that if we ever encounter beings who perhaps are from another planet who we want to communicate with, it's likely the only human language that we will have in common will be mathematics. So it is a very exquisite construction. So Einstein's score told us space and time bend. So here's a little cartoon. It's easier for me to show you this than it is for me to actually work out all the details of the scores that show you this. And I've used this image many times, even in teaching students. It turns out the most effective way to open the doors for students studying physics is all through the visual. Now, there's a reason for that. At least the neuroscientists tell us that a large part of the human capacity to process data processes visual data. And so if you want to communicate with people effectively, that statement about a picture is worth 1,000 words, that's actually a scientific statement about information exchange and how humans interact with information. Here's another picture. This one, except it looks like it's not going to work, so I'm going to go past that one. This was actually an animation of the coalescence of what are called neutron stars. These are the sources of some of the waves of gravity that scientists have been detecting over the course of since 2017. And this is actually a Fermilab movie. I don't know why it's not working, but you know, sometimes technology fails. But we have been talking so far, I and all of the previous speakers on the science part, about how science can influence art. Our speaker who made the Arctic pictures asked the physics questions in terms of being in the Amazon. The question, you know, in some sense, what we're looking at there is, what does something like physics do to art? But there's another part of the story which I have lived the last decade or so of my life that I want to tell you about. And that is, what does art do to physics? It turns out it has an important effect. Now, one person who was aware of this is the person whose quote you see at the bottom of this screen. Albert Einstein, I like to call him Uncle Albert. Albert Einstein said, after a certain high degree of technical skill is achieved, science and art coalesce in aesthetics, plasticity, and form. So I'm going to show you some pictures. These are pictures that I developed from studying some equations about 15 years ago. And because the equations, the thing that is interesting about equations for those of us who use them is we can see patterns in the actual equations. Now, explaining these patterns even to each other is often a challenge, but if you can convert those patterns into pictures, then you have a better way to explain them. And I've been doing this, like I said, for about a decade. So here's a set of very simple pictures that came out of a set of equations that I and a colleague named Michael Fox were studying around 2005. And so we looked at the pictures, and in mathematics, these pictures are actually called graphs because they have mathematical rules that describe how you construct them. So we said, well, let's see what we could do if we just play with those rules. You can get to this object using the same rules that came from these simple pictures. And so we continued this process of studying the pictures based on the same set of rules. So here's an object that comes from that picture-making process. Of course, we use computers because at some point, it gets beyond your capacity to write things on paper and pencil. So you have to use computers, and we'll come back to that. Here's another set of images. These are my favorites, by the way, in this picture-making adventure. Here's another, and another, and another, and another. And so all of those pictures start off as equations. You know, they convert themselves into relatively pleasant-looking images. So when Michael Fox and I first discovered this capacity, and by the way, this is in service of answering some of the questions that were alluded to earlier. It's quantum physics. So we're after understanding quantum mechanics and general relativity and space and time and all those things that we heard in our previous talk. That's what we're studying with the equations. But we understood that there's this other hidden layer behind the equations that you could study. So I've been basically working the last decade or so with some of my student collaborators are actually here in the audience on this idea about studying mathematics by looking at the pictures behind the mathematics in the service of trying to figure out how quantum gravity works. So when Michael and I first discovered this process, we gave these symbols a name. We called them adinkras. Adinkra is a word that comes from West Africa, and it basically describes a tradition in West Africa where symbols have hidden meaning. Well, that's exactly what we're doing. These pictures we have hidden mathematical messages buried within them. So I'm going to take you to my world of adinkras, but first I'm going to show you the mathematics. You know, we physicists can't resist that. So for people like me, we look at equations like this and we scratch our heads for a little bit and we talk to our friends, like for example, my colleague, Professor Alexander out here. We talk back and forth and finally we say, what does that have to do with what goes on in the laboratory or in an experiment or in an observation? And then eventually we settle it. And so here's a mathematical answer. Well, there's a 40-year-old problem that even some of my smart friends couldn't solve. So I decided to look at them, and this is what they tell me. I say, oh, that's pretty terrible. In fact, it's so terrible that even they don't know the answers. But I've got a secret weapon. I can use pictures. And so here at Brown University, 2 years ago, working with two students, Yangre Hugh and Hazel Mock, we decided to take our picture-making process into the equations to see what came out. And so we do things like we learn how to multiply by pictures by pictures. That's something that physicists do. And we constructed this object, and I'm only showing you the first layers of it because it's actually 32 layers tall. And we actually talk to computers. So this is what the computers tell us. But because we know how to convert the data into the pictures, we were able to answer a question that even the smartest physicists in the world had not answered for 40 years, and it has to do with quantum gravity. So you see, art can be directly used in theoretical physics as a tool that goes beyond the equations that one encounters. That's boring. It's just a little bit better. This is how we talk about the physics of chemistry. And then finally, I'd like to tell you that the use of computers is like putting on glasses. It gives your mind the power to go out and cover more mathematics than you can ever dream. And I have one final dream that I'll leave you with. Namely, that it is my dream that if we humans interact with mathematics long enough, it will turn out that computers will be thought about as the same as musical instruments. There are geniuses at playing musical instruments who don't read scores. So imagine a world where you don't have to go to school for 12 years to do great mathematics, but by playing with a computer, who knows what boundaries you will break in discovering theoretical physics. Thank you.
When I actually go, I can speak now, right? Call my colleague at Gatesville to come. He spends his life trying to actually measure, what those pictures told us, okay? We don't know mathematics and pictures. Try to prove, find out who's right.
There we go. Thank you so very much, Vesna. And thank you so very much to all the previous performers that we've seen. That was, I'm feeling definitely at a higher level at this point. And it does sort of take us into a theme which I probably should say, which is, I think let's all take a moment to really enjoy what we've been experiencing. Let's try to be calm. Let's try to be quiet. And what we're going to do is try to create some inner peace. Because, quite literally, inner peace is a necessary requirement of the type of research, the type of good physics that I'm doing. The physics is specifically targeted at rare events. We're trying to understand the outermost aspects of physics, pushing the edge, and the way we're doing that is by looking for incredibly rare events. Can you see them? Have you achieved enough peace internally now to begin to see those rare events? And what's stopping us? What's stopping us from seeing those rare events? Well, one of the things that's stopping us is these incredibly violent events, cosmic rays. As a physicist, when we try to conduct an experiment, we become brutally aware of the incredible violence that is taking place outside of our atmosphere and the way in which these particles are bombarding you. Right now, every one of you, hundreds of cosmic rays are traveling through your body every second. If you hold out your hand, one cosmic ray per second, it's the sort of standard reference. Every second. And most cosmic rays carry electric charge, and as a consequence, it means they really want to interact with you. They are violently interacting with your molecules. Although that's not a problem because life grew up in this environment, and as a consequence, your systems, your biological systems, the way you evolve, multiply, repair yourself, those all work with that. But it's something as a rare event physicist that we have to do something about. So let me take you on a journey where we can get away from these cosmic rays. It's a journey that is going to use a deep underground laboratory. What you're looking at right at the moment is not actually the main lab. The main lab is deep underground. Those green shafts are over a mile long. And what we're going to do is get into an elevator, or cage as it's referred to, and we're going to go down. Now, we're joined here in this scientific work that requires a large number of people, a small fraction of whom are shown here, although thanks to COVID protocols at the time this picture was taken, you can't recognize anyone. But what we're going to do is descend down in the cage And what will happen is you'll achieve calm. Because every 20 meters every 200 meters you descend down through the rock, that overburden, that shielding is going to reduce the cosmic ray flux by another factor of 10. Every 200 meters, another factor of 10, another factor of 10. So if we descend 1,600 meters, a mile, the cosmic rays are now being very, very effectively blocked. If you hold your hand out, you'll be waiting a month for one cosmic ray now to go through your hand. Peace. Peace returns. Except you. Your natural radioactivity came with you as you went down this mile journey underground. You're now acutely aware of the fact that you carry quite a burden of radioactivity. Not just one event per second, but thousands of events every second inside your body. Again, don't be alarmed. It's something you've grown up with. It's something that human life is quite used to. But nonetheless, if you really want to achieve this inner peace that we need to see the rare, we're going to have to do something about this. So our physics experiment will have to be separated from us. Now, water can be purified to better than 1 part in 10 to the 18. That's 1 with 18 zeros after it. That's incredibly pure. So the best way to isolate an experiment from humans who are issuing thousands of gamma rays every second, you're all radiating one another right now, the way that you're going to do this is put, say, 4 meters of water between you and your experiment. And all of that gamma radiation will be absorbed, and now you're achieving something closer to the peace that we are looking for. We're trying to create the quietest place on Earth, the quietest place possibly even in the universe, in order to see these very rare events. So let me just take you on my own journey in physics, which is age 10, scantily clad, in a bathroom, floor covered in water, a shower hose disassembled, the head removed, and I'm sketching with a Chinograph pencil, trying to understand on the tiles what is influencing the trajectory of that water. How do we describe that motion? It was something I knew there had to be an answer for, but couldn't figure it out. What I later learned to be a parabolic path. As it turns out, it was simple, artistically beautiful. You just separate the motion in the vertical and the horizontal. The horizontal is unaffected. The vertical is a constant, not in the motion, not in the velocity, but a constant in the rate of change of the velocity, or the rate of change of the position. A single number g describes that system. Well, if I put you in a situation I was as a graduate student, which is another single fascination developed, which was simply, what is the universe made of? And it turned out that the stuff you and I are made of, baryonic matter, is just the flotsam and jetsam, the 5% of the universe. The vast majority is something else, and the question is, what was that, or is that something else? It appeared to have a tremendous opportunity, a grand example, a grand answer. It turns out our universe is dominated by dark matter, and that at the time I was sitting sort of where you are, if you're a graduate student, we thought the universe basically over time, running left to right, just would exploded as a big bang, was going to expand to some asymptotic level and then start collapsing again. And that all seemed very natural, although as I subsequently discovered in my time as a postdoc, we had to completely overhaul that model. In fact, a new component, a dark energy, was going to blow us all apart. We would initially start expanding and then slow down and then speed up again, and that is where we find ourselves right now. These two components are vying for preeminence, the dark matter and the dark energy. You and I, flotsam and jetsam, we're just the 5%. And no, when one stands up and talks about dark matter and dark energy, of course, you feel like you're part of this MCU reboot or something. These are genuine scientific terms. Dark energy is a property of the vacuum itself. Dark matter is something that brought us all together. It formed our galaxies. It formed the clusters, but it is incredibly ubiquitous. In this hall we're in at the moment, there are tens of billions of dark matter particles. If you hold your hands out right now, you have a dark matter particle in that volume. But the question is, what is that material? And this is where I want to just sort of move to the art almost. This is a 10-gram detector that I made with colleagues when I was a graduate student. And we were attempting to see the dark matter by having direct collisions with this particle, with this event. And this type of technology, this superconductor, has led to all sorts of new technologies that we've used, in new detector designs and quantum. These are quantum tunnel junctions. So a number of applications. And it was merely a size of a thumb. It's 10 grams. Unfortunately, we have not seen anything. We took it out of the ground. This is our underground laboratory on the way to work. Achieved the quietness and nothing. So we scaled it up. This is now a 7-ton detector. So we went from 10 grams to 7 tons, and we did this over the last 30 years. And this is what is now necessary in order to try to test the dark matter. In these incredibly peaceful places that we have created, we are looking for the occasional interaction of a dark matter particle. And that, briefly, is really what myself and many other of my colleagues are doing for the love of physics. Thank you.
Okay, so thank you, Rick. I just want to, if you can give me slides of Leo's slides. I just want to end. We heard from theorists how they're trying to understand nature with this computer and see it, or tell us what to search for. And thank you, Rick, for really explaining what you do for the love of physics, trying to understand the inner workings of universe. But I also wanted to make a comment how, I know that for majority of us that are doing something boring called condensed matter physics, really boring name, and go back to, it was actually, no, this one, yeah, right, that, yeah, thank you. So, and thank you, Leo, for your wonderful presentation. So I just want to go back to kind of say what a lot of us do, condensed matter physicists for the love of physics. And before Dolby Illustrator power and people like Leo, we could never actually picture what we do and make. I'm trying to get that slide back. So we could not make these pretty pictures until about 10 years ago. Just we didn't have a computer power or, those instruments that he showed you to make these devices. And what is our love of physics is to try to understand or force electrons by either manipulating material structures to behave in the way we want so we can use it. And thanks to people like Leo and these devices, we actually have the most important thing of our life, our iPhone. If it wasn't for that, you would not be able to turn off your iPhone with the speed of 5 gigahertz. Just to name a few. And this is kind of a lot of us nowadays, I know, work to apply some of these principles to really solve the issue of energy and global warming, and this is, and again, give us amazing machines like quantum computers so that we could make you pretty pictures even faster, Jim, right? And understand nature. So just to kind of give a perspective on that as well. And then if we can stay in a room another couple of minutes, I would call Stefan Alexander, because we had to cut Stefan actually short, but to tell us about physics of music. Please come, and then that would be, yes, the last presentation.
Yes. First of all, I want to, yes, oh, mine is coming up?
Your presentation is here, if, sorry. I clicked on the, oh, there it is, yeah, it's right there. Yeah, here we go.
Yeah, let's, first of all, thank the staff of the physics department, especially Angela Johnson, our chair, Vesna Mitrovic, and Valerie and others for making this happen, and the students. All right, so yeah. So this is the title of my little talk here. You know, when I was younger, I grew up in a musical family. I was expected to be a professional musician. Got into this high school of performing arts and all that good stuff, but I didn't go. I wanted to become a scientist. But all throughout, I continued playing my music and continued exploring that. And it even got to me at some point, I don't want to get into a long story. I lived in London for a couple of years, and there's a famous musician, I won't name drop him, but he said, you should just leave science and just come work with me in the music world. And if I told this person's name, you'd be like, you're crazy, you should have done that. But I continued on the path and, for the love of physics. And then I learned something. I had the pleasure of teaching a class with a historian of science named Rick Kramer at Dartmouth when I was at Dartmouth, and we taught this class for a couple of years. It traced the history of physics going back to 580 BC all the way to now. The history of the development of the ideas. I learned something very surprising that I wish I had known, and when I was younger, and with the struggle, trying to understand being a musician and what am I? You know, I was confused. By the way, I still am. I shouldn't be telling that, right? Justin, that's not a good idea. Here's what I learned. What I want to do is to talk about harmony in physics and music. 5 minutes. I got 5 minutes to talk? No, I don't think I'm going to get this is not possible to do this in 5 minutes. Okay. Let me just skip this quote. This is a letter. Albert Einstein had a friend named physicist Robert Thornton, and this is basically the idea. He's expressing this idea that it's not enough to stay in your silo as a physicist. If you want to break new ground, you need to explore other ideas. You need to explore philosophy and the arts. But when I talk about harmony, what do I mean? But when we say something is harmonious, it's not just in the context of music. We could look at, for example, interconnectedness. Back in the days, Jim worked on something called Calabi-Yau manifolds, which is a geometry and string theory that relates the different particle species to each other in a way that is purely geometric. And so that's a little, computer-generated picture of those equations. Beauty and unity. So things, for example, we had space and we have time. They're two separate entities. But the four-dimensional space-time continuum unifies and harmonizes space and time in new ways with new predictions. Balance. We look at the individual elements, and these elements come together and they balance each other out. So what does this have to do with music? The first thing I learned that blew me away was that 580 BC, when the Pythagoreans came on the scene, music was actually the first experiments that were used to try to understand the concept of the music of the spheres. The ancient Greeks believed that the planets actually, and the model of planets move in their circular orbits, were in a harmony having to do with whole integers. So the planets were playing a musical harmony, and this tradition of trying to understand The mechanism for planetary motion lasted about 2,000 years. There's a whole long history, but it basically led to the basic picture here of when we talk about musical harmony. What Pythagoras discovered was that if you take a vibrating wave, for example, if I take the string, this instrument, or our friend, the guitarist, when he plucked the string, there's a fundamental. Let's, for example, I'm now going to do it because I don't have my saxophone now. It's going to take time because I have -5 minutes. But this is so important. I really want the students especially to get this lesson behind before, it's going to be so cool. Trust me. So the fundamental frequency is, let's call that the note C. Da, right? If the octave, let's not pay attention to that. The octave is the ratio 1/2. If I split that vibration in half, I get da, right? But the most important one, the most harmonic, and I think all the musicians here will agree with me, is what we call a dominant or the perfect fifth. Ba, 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 right? So 2001 Space Odyssey. A lot of music, Western music and jazz music, is based on the movement from the dominant to the tonic, or the one, right? A lot of the harmonic movement is that. It's very important to talk about that because when Pythagoras did this, he set off course with Aristotle and Plato to find this harmony through perfect geometry, perfect spherical geometry. So the Ptolemy and that whole system, the Alchemist, right, this huge book written by the Arabs to try to understand these epicycles, didn't work. Then Kepler comes on the scene in the 1600s. You see in his book, he spent 20 years of his life trying to understand, and he had to give up these perfect circular motion. He wrote down notes associated with the planets. He was looking for the perfect fifth. He was looking for the 2/3. Remember, that's the ratio. He didn't find it. But during that time, musicians at that time were working on, the avant-garde composers were working on polyphony. So they're playing, instead of individual scales and notes, they were working on many notes played at the same time. So all of a sudden, eureka moment, he embraced that, and he found the perfect fifth. You see that equation there? 2 and 3. This is the first time a human being wrote down an equation that had this idea of harmony. Not only in the perfect fifth, he found the perfect fifth, but that's the equation of an ellipse. And that equation is universal. It didn't only apply to one planet, but for every single planet in our solar system. T is the amount of time it takes a planet to go around this ellipse, the sun. And this R is basically the distance the closest to the sun. And if you know 1 and you square it, you can predict the distance away for any planet. And in fact, we use the same equation now, the Kepler satellite, to now find billions of exoplanets out there. And this led Isaac Newton, Fourier, and D'Alembert, I can't pronounce his name, to come up with the wave equation. I'm going to now end with music. So musicians are also inspired by the discoveries that physicists made in understanding the inner harmonies, not only just in sound, but how this has to do with the basic building blocks that Jim talked about, and Vessner and Leah Lee talked about as well, in matter. So you have a musician like John Coltrane who studied the works of Albert Einstein so deeply that he also came up with his own geometric rendition of higher musical harmonic forms. I'm going to skip to that. I'm going to skip and, of course, show you the result of thousands of years of human ingenuity. These equations, one is a Schrödinger equation, and the other one is, of course, the wave equation, which some of you will be engaging with in the midterm this weekend. And now, I'm going to end with this. This is a picture of our early universe. It looks gobbledygook. It's supposed to be vibrations, energetic vibrations at super high energies. And then later on, it forms this stuff here, which you're like, what's that? But later on, if you focus in, you find a beautiful sombrero galaxy, one of many species that we inhabit. And this is basically what it looks like. The origin of the universe, at least back then, is nothing more than a vibration, right, of a sound vibration, actually, literally. Every dot here you're looking at is a galaxy, about 2 billion. This is a little snapshot, most recent data. And I want to end with something really cool. Now, this is really going to bug all y'all out, all right? Look at this. I'm going to ask Jim to explain a little bit of, just in one word, what that is. That's right. This is a mathematical geometry that predicts, basically, that geometry encodes all, basically, the different states of nuclear matter. Look at this. So give up the labels. Forget about those labels. Just look at the geometry. If you draw that picture, you've summarized those particles. Same exact geometry. Leland Baker, what does that look like? Circle of fifth and the 2-5-1. It encodes the same geometry, encodes all these beautiful harmonic relationships. Thank you very much. That's all I have to say.
Thank you, Stefan, for this amazing unification, grand unification of music and physics. So I really want to thank everybody for coming tonight, and I hope you really got to enjoy and appreciate at least why we all do physics and art and music, with a common goal, I guess, to understand the nature around us and to make our lives better and more fun. Depends what you define better. For some, it's just more beautiful. For others, it's more practical. You know, we need our iPhone, right? And anyway, so thank you, and I hope you really enjoyed it. So we're gonna move now to talk to our guests, outside. Thank you.